Anybody have science courses in school, in grade school or high school? Okay. What was the definition of matter? Put you on the spot. It's a really simple definition. Matter. Anything that has mass and occupies space. Okay. That covers just about everything. Except for dark matter. What's dark matter? You heard about that, dark matter? I don't know what dark matter is. I don't think they know what it is either. All right, this is just an outline. These are the topics we're going to cover. I just put that in there for the recording purposes. All right, what's chemistry? No guesses? No, you can't, don't look. Chemistry is the study of substances and how they change from one substance to another. When we say change, that's talking about the identity of the substance. What identifies this substance as different from some other substance? It might have different boiling points or melting points. It might have different chemical reactivity. It might be non-reactive with some things and reactive with others. All of those play into what is the identity of that substance. And then we study how this is transformed into something else. Chemistry is a very broad topic, covers a lot of ground. And it's broken into lots of subunits, right? So if you're going to go to dental school, you'll probably have to take organic chemistry, right? Okay. Now, that brings up a question. Is an introductory chemistry course going to be sufficient? Or do you need the 2-semester version? One semester I had a student in here that was registered in this class and found out that she needed the 2-semester to go. So if you've researched that and you know that this is going to satisfy, then we go for it. Probably because it has a lab associated with it. Yeah. Okay, back to the topic. That's chemistry. So there's our matter. Matter could be anything. It could be living, non-living. It could be characteristic of matter is its mass. Right? We know what mass is. I may have a slide on that, but sometimes stream of consciousness works better. So what is mass? Mass is an expression of how much there is, which means that anywhere in the universe, 1 kilogram of substance is going to be 1 kilogram anywhere you look. Well, except for close to black holes. Right? Then you're getting into relativity and you have the difference between rest mass and relativistic mass, and we're not going there. Right? We're going to say that mass is mass is mass. It doesn't change no matter where you go. How about weight? Weight is a force. And a mass in Earth's gravitational field will give a certain force, right? I may weigh 200 pounds on the Earth's surface, but I'm the same mass if I'm on the moon's surface, but I'll only weigh 1/6 of that, right? About 33 or 4 pounds. We've defined what matter is, but we can't leave out energy, right? You can talk about the entire universe in terms of 2 things, matter and energy. Now, of course, Einstein said they're both equivalent anyway, right? E equals mc squared, right? Matter and energy are interconvertible. But for chemists, we make a distinction. There's matter and then there's energy. And energy can manifest itself as heat or as light or electricity. I heard a good joke the other day. We got any Democrats in here? Okay, I don't want to offend you. But what did Democrats use to light their homes before candles? The answer? Electricity. Okay, enough of that. Okay, that's just a reinforcement. So when we observe matter, we can see it in one of three different phases for our purposes. There are a number of different phases possible in the universe, but for our purposes, we're going to stick to solids, liquids, and gases. Right? The closest fourth phase to us is on the sun, plasmas. Or if you go to a muffler shop, right, and they use their cutter, that's a plasma cutter. And it'll go through a steel tailpipe like a hot knife through butter. So you don't want to get your fingers in the way. But we're going to focus on solids, liquids, and gases. Now, when we identify the phase of matter when we start to write elements and compounds and then write our sentences, chemical reactions, sometimes we want to say, what is the phase of the matter that's in this reaction? And for solids, we will say like that, put that next to the compound, like sodium chloride, table salt would be a solid. Or we might say liquid, right? If we have water, would be a liquid at room temperature and 1 atmosphere pressure. Or we might have that nitrogen. 78% nitrogen is what we're breathing right now. It's in that form, and that gives its phase. The only other, it's not really a phase, it's a descriptor, would be if we are talking about a solution. And the solutions we're going to talk about are in water. So we would say AQ for aqueous solution. Those are the only added parts to the compounds and elements that we're going to use. All right. So what is a solid, a liquid, and a gas? What differentiates them? This might seem trivial, but solids have a definite shape and a definite volume. So, right, that's a solid. It's not a pure solid, but it's solid. It holds its own shape and it has a definite volume. Doesn't need a container. Liquids, on the other hand, have a definite volume, but they don't have a definite shape. They need a container to hold them. And there is microscopic reasons for that. Okay, when you're trying to describe something that's happening in a chemical terms, I lost my train of thought. Back up. Right. It'll come to me later when I'm not trying to think about it. Go back to liquids. Indefinite shape, definite volume. Gases, on the other hand, have neither a definite shape nor a definite volume. They fill the container you put them in. So the container has to be, if you want to confine a gas, it has to be a container that's sealed, like a balloon. Put a gas in it, and it assumes the volume and the shape of the container. Oh, now I remember. When we think of chemistry, trying to decide what's happening in chemistry, in a reaction, for instance, or in a physical transition, we look at it in terms of the macroscopic, what we see is happening, but there's always a microscopic interpretation because what's happening is based upon atoms and molecules. What are they doing? So that's the type of intuition that you should try to develop, right? When you see something, when you see a color change, say on the microscopic level, what caused that color change? So here are examples, right? There's a $50 with Eisenhower's profile on it. Then there's a liquid. I'm not sure what that green liquid is. The one on the right, of course, is a gas. That's probably a halogen, maybe chlorine, probably chlorine. So this phase or state of matter is dependent upon various factors. One is temperature. Right? If you take a solid like ice and increase the temperature past 0 degrees Celsius, then it's going to melt. It's going to go from a solid to a liquid. And if you increase the temperature further to 100 degrees Celsius, you're going to start getting a gas. It's going to boil. But for transitions between liquids and gases, pressure is also significant. Pressure going from a solid to a liquid or a liquid to a solid, pressure is not as important. It still has a place, but it's more important for gases and transitions from liquids to gases. So you have temperature to deal with, you have pressure to deal with. Those are external forces or conditions. And then you have internal forces that are involved. In other words, how strongly do the molecules attract one another? If the strength of attraction is very strong, then it's going to take more energy to convert a solid into a liquid because you've got to break those intermolecular attractions. So the attractions between water molecules are very strong. So that's why water is liquid on the surface of the earth. Right? If you didn't have those strong attractions between water molecules, water would be a gas. And then we'd all be in big trouble. Or say dry ice. Everybody know what dry ice is? Well, you've probably seen it. It's solid carbon dioxide. Okay. So what happens when you take a piece of dry ice and drop it on the table? It starts smoking, doesn't it? Well, that's not the carbon dioxide. It is converting from a solid directly into a gas. That's called sublimation. But the reason you can see it is because it's so cold, it condenses moisture out of the air. And that's the fog that you see. So that's why if you want to create a fog like for a Halloween fun house, take some water and get some dry ice and throw it in the water. And it'll make a lot of smoke. It won't be hazardous, but it'll give you that smoke for your scary house. All right. So what is a property? Think of a property as key to the identity of a substance. When we describe a property, we are differentiating this substance from any other substance. For instance, if we say this substance is solid, that's a property. Okay? Or if we say this substance is combustible, right? If you have lighter fluid and you squirt it on the table, it's combustible. It's not doing anything right now. It just describes what it's capable of doing. Its potential. It has the potential to catch fire. That's the first one, the phase change, say it's a solid, or it melts at 0 degrees Celsius, melting point, that's a physical property because it does not change the identity of the substance. It doesn't describe a potential for change of the substance. That's a physical property. If we describe a chemical property, then we're saying it has the potential to change into something else. So the chemical property of that lighter fluid is that it's combustible or it's flammable. That's a better term. It's flammable. That's a chemical property. It has the potential to burn. We're not saying it's burning. It's not burning right now. It just has that potential. That's a chemical property. Right? Various physical properties descriptive terms like color, odor, the state, I already mentioned, melting point, boiling point, hardness. Right? When we say, what's the hardest natural substance that we know of? It's a girl's best friend, right? Diamond. Diamond's the hardest natural substance that we have. On the Mohs scale, it's a 10. So that's a physical property. Let's see. Yeah. Physical properties. When they describe the substance, the physical property does not imply any type of change of identity. That would be a chemical property. That's all that slide is trying to say. Okay. So if we say copper objects turn green in air, that's a chemical property. They have the potential to change from copper to something else. So have you ever seen buildings with copper roofs on them? No. I was a graduate student at LSU in Baton Rouge, and I don't know what they call it, the barn, the building where they had rodeos and animal shows, had a copper covered roof on it. Well, they replaced that roof while I was there, and it was bright, shiny, just like a new penny. And pretty quickly, it started to get dull. And then several years later, right as I was leaving, I noticed that it was starting to turn green. So it went through stages. They call that the patina. And some of the buildings in Europe are centuries old with copper roofs. And they are gorgeous to look at, the color that has developed over time. That green color comes from a change of copper, a chemical change, right? The property that copper has the potential to turn green is the property. Let's see. Decomposition, I don't know why we put that term in there. Triggered by the presence of energy. You can decompose something by adding energy. What you're actually doing is breaking bonds. Let's see. Right. Okay. There's the Statue of Liberty, which is copper clad. And it has that green color. Let's classify each one of these as physical or chemical property. Iron metal rusts in an atmosphere of moist air. Chemical or physical? Chemical. Right? It changes its identity. It has the potential to change its identity. Mercury metal is a liquid at room temperature. Silence. In the broadcasting industry, we call that dead air. That's a physical. Nickel metal dissolves in acid to produce a light green solution. It has the potential. That's not worded correctly. Nickel metal has the potential to dissolve in acid and produce a light green color. That's a chemical property. Now, when we talk about change, we're actually describing a change of the substance. If the identity of the substance is unchanged, then any change that occurs to it is physical. Okay, so when we boil water or freeze water, we haven't changed the identity of the substance. It's still H2O, but it's now in a different phase. That's a physical change. A chemical change, on the other hand, describes an actual change of identity for substance, like iron rusts in moist air. I grew up in Atlanta, and downtown we had a couple of teams, sports teams that were had varying degrees of success. One was the Atlanta Flames. I don't think they're there anymore. They were a hockey team. And the other is the, let's see, what's the basketball team? Hawks, thank you. But they shared a new building. The architect for that building had one bright idea. He knew that the reason that aluminum cans will throw an aluminum can out there and it'll be there 100 years later. Aluminum is a very reactive metal, but it's so reactive, it forms an aluminum oxide coating on it that prevents moisture and air from getting to the underlying metal. So it protects the underlying metal from further changes. Stainless steel is like that. Chromium, you mix, I think, upwards of 18% chromium in steel, and you get stainless steel. Well, chromium is very reactive. So if you scratch the surface, it's instantly going to form chromium oxide and seal the damage. So the underlying metal no longer, it can't rust. Well, this architect said, there's this new building material on the market. And I'm going to put this on the roof of the building was called the Omni. And it was a type of steel that rusted very fast. And he said, when it does that, it's going to seal the underlying metal, right? So air can't get to it, just like all these other examples. What he didn't take into account was rust is less dense than the metal. So it expands. That's why when you see a car or a tractor in a field that's been there for a few years and you look at the rusting parts, they flake because as the rust forms, it expands and it flakes away, exposes the underlying metal. It just continues to rust until it's all gone. So what this architect didn't realize that when you rust on the surface of the roof of the Omni, and it makes this bright red brick color, it's pretty to begin with. Well, it expands, right? It doesn't actually seal. It just sits on the surface, and Atlanta gets between, it's 35 and 40 inches of rain a year, right? So when it rains, all that rust runs off the roof and onto the concrete, and it produces these nasty red streaks everywhere. So after a few years of tolerating that, the owners of the building decided, right, this is costing us money. So they tore the building down, built something else. But that was a chemical change on the roof of that building. Right? Iron rusted. All right. So, how do we know whether it's a property or a change? Well, a property is a descriptive term that does not describe any type of change. It's potential. It describes a potential. Whereas the change describes the actual movement from one to the other, but the identity remains constant. The identity does not change. Right, we can say the same thing about the chemical. Properties are potential, changes are actual chemical reactions that give you a different substance, the change of identity. Decomposition is the one we looked at before. All right. So which one of these is a chemical change? When you pulverize rock salt, you still got salt afterwards, don't you? That's a physical change. You just change particle size. Burning wood. You change cellulose and lignin, the primary components of wood, into carbon dioxide, water, soot, and ash. So burning wood is a chemical change. Dissolve sugar in water. That's a physical change. How do we know? Because the identity of the water and the sugar are the same. We can get them back. All we have to do is evaporate the water. There's your sugar. Didn't change. Melting a popsicle on a warm day, you're just changing the phase. All right. So what's a pure substance? It's a single kind of matter. It could be an element. It could be a compound. That cannot be divided into two or more other substances. In other words, no matter how you try, you still got the same substance you started with. Water is a pure substance. Sucrose, table sugar, is a pure substance. What's a mixture? Mixture is a physical combination of two or more pure substances. So sugar water is a mixture, right? It's got water and sugar in it, and they retain their identities. There was no change of identity when we put them together. Salt water, right? That's a mixture. The air we breathe is a mixture, primarily nitrogen and oxygen gases. Okay? Mixtures can either be homogeneous or heterogeneous. Those prefixes are from the Greek. Homo means same, and hetero means other. So homogeneous mixtures have the same composition no matter where you look in the mixture. You can take a subsample anywhere and the composition will be exactly the same. The percentage composition of your pure substances will be exactly the same no matter where you look. That's a homogeneous mixture. And a homogeneous mixture is also called a solution. Okay, so the air we breathe is a solution. Let's see. Carbonated beverages, that's a solution. It's got water. It's got, used to have pure cane sugar in it. Not anymore. Now they put, let's see, what's the proper term? High fructose corn syrup. Right? It doesn't have the same flavor. You ever notice that? You guys are probably not old enough to remember real Coke. back before New Coke, right? It had sucrose in it. You can still get it from Mexico. Coca-Cola made with cane sugar. It's a different flavor. Anyway, it's a solution. It's a homogeneous mixture. A heterogeneous mixture has visibly different phases. In other words, the composition varies from one place to another in the mixture. Examples, the jar of jelly beans. You see lots of reds over here, lots of blacks over there, some greens here. It's not uniform throughout. That's a heterogeneous mixture. So this is just a flow chart. If you like flow charts, organize your thoughts. Which of the following is homogeneous? Okay, now we're talking about problem solving. With this question, which of the following is a homogeneous mixture? These types of problems I work backwards. Which ones are mixtures? Pure water? No, that's a pure substance. Throw it out. It's not a mixture. Copper metal? That's a pure substance. Throw it out. You don't even have to deal with it. Now let's see which one's homogeneous. Gasoline, jelly beans, and soil. Well, we already said jelly beans was heterogeneous. My PhD is in soil science, so you can take my word for it. Soil is heterogeneous. Just go to any road cut. That's not through rock, of course. Around here, it's kind of hard to find those. But if you can find a road cut that's through soil, you can see profile. Different colors, different textures as you go down. That soil is heterogeneous. The only homogeneous mixture here is gasoline. It's primarily octane, which is a hydrocarbon. And then nowadays, you've got about up to 10% ethanol mixed in with it. And then you have other additives that the manufacturer says will keep your carburetor and engine clean. Not carburetor anymore, right? Fuel injectors. I'm showing my age. Which of the following contain only pure substances? Okay, in this one, you've got multiple choice, and you're looking for all of them to be pure substances. So anyone that has a mixture of any kind, throw it out. So A has a glass of tea. That's a mixture. Right? B has glucose. That's a mixture. Throw it out. C has glucose in it. Throw it out. Pure substance, gasoline, dirt, rock, none of them have only pure substances. Unless I missed something. Oxygen, tap water, glass of tea is not a pure substance. Oh, sorry. B. Oxygen's pure. Glucose, right? The blood sugar, right? Anybody got diabetic or have diabetics in your family? They have to check their glucose, right? The blood glucose. If it rises above a certain level, then you're in danger. And silver. These are all pure substances. I blew past that one. Sorry. Now, what's an element? Well, elements have been known since antiquity. They may not have been called elements, but they were identified as such because they could not be reduced any further. They're pure substances, but pure substances can be compounds. In other words, they can be reduced to other pure substances by breaking bonds, like water. We can turn water into hydrogen and oxygen using an electric current. It's called electrolysis. But elements are pure substances that cannot be reduced further by either physical or chemical means. So gold, silver, copper, those are pure substances. Those are elements, excuse me, those are elements. All right. Compounds, on the other hand, are combinations of two or more elements. So if we put together, say, two atoms, and one of them is carbon, and the other one is oxygen, we get the deadly compound, carbon monoxide. If we put together two nitrogen atoms, we get diatomic nitrogen, which is not a compound because they're the same atoms, they're the same elements. Oh, by the way, those, the list of elements I want you to memorize, you know, some of them have blue shading in the background. Those, you can memorize the symbols, but when a problem says react hydrogen with oxygen, what it's saying is you want the stable form of hydrogen and oxygen at room temperature and pressure, which is they're diatomic. So those blue ones are all diatomic. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are diatomic elements. So you need to know that, not just the symbol, but you need to know that they are diatomic when we are talking about them in terms of chemical reactions. So that if a word problem tells you to react one of those, then you know to write it diatomic and not single element. Okay? So compounds have to have two or more elements in them. All right, there's another flow chart. Compounds, as a general rule, have properties that are distinctly different from the elements of which they're composed. So hydrogen's a gas, oxygen's a gas, but put them together and get water, water's a liquid. Plus, hydrogen is reactive as a fuel. Oxygen is reactive as an oxidizer. Put them together in a rocket engine and you blast into space. But put water in that rocket engine and you get nothing. It's not reactive. Compounds can have the same elements in them, but in different proportions give you different compounds with different properties. So if you have, say, water in that ratio of hydrogens to oxygen, and you have hydrogen and oxygen in that ratio, you get two different compounds. That's water, that's hydrogen peroxide. Okay? If you put water on a cut, it just gets wet. You put hydrogen peroxide on a cut and it fizzes. It's called chemical debriding, right? And it fizzes because damaged cells release an enzyme called peroxidase. And the peroxidase converts that into water and oxygen. And the oxygen is what kills the bacteria in that wound. Now, you don't want to use hydrogen peroxide on a wound, but just once when it first happens, because it is an irritant. And if you keep using it on the same wound, it'll never heal. So just use it one time to clean the wound and then go to something else like a bandage, stitches, bacitracin, you know, that type of stuff. Okay, back to the topic. Compounds have definite composition. In other words, a compound is a pure substance with a definite ratio of elements in the compound. Whereas mixtures have variable composition, can have variable composition. If you say make sugar water, that's only like a teaspoon in a gallon. Or if you're making sugar water for your bird feeder, your hummingbirds, you're going to put 50-50, right? You're going to put a cup of water and a cup of sugar. Will that go into solution? Anybody ever made hummingbird feeder juice? It goes into solution, doesn't it? Right? It's very, very soluble. Mixtures can be separated using physical methods like evaporation or filtration or various other things, chromatography. Compounds cannot be separated by physical means. The elements in a compound can only be separated by chemical means because you have to break bonds. All right. There's another flow chart. You can use them, take it or leave it, right? So when we're classifying a sample of matter, we'll ask questions. Does the sample of matter have the same properties throughout? Are two or more different substances present? Right? Is it a mixture? Can the pure substance be broken down into simpler substances? That means, is it an element or is it a compound? All right, I'm going to skip that one. All right, let's look at elements now. We've defined what an element is. How many are there? We have identified or created 118 elements in the periodic table. So organoson is the 118th one. That's prepared in a nuclear reactor in minute quantities on the order of atoms worth. It's very unstable. In fact, most of those heavy elements are unstable. We call them radioactive. They decompose into other elements. But there are 118 elements. 88 of them occur naturally. There might even be more than that. The reason you would have more occurring naturally is because over time, we've developed better analytical techniques. So we can take natural sources and find those elements that were once produced artificially are now identified in very small quantities in nature. But roughly 88 of them naturally occur and 30 of them have to be synthesized. All right. When we're counting atoms, right? If you count atoms throughout the universe, that would take several 100,000 lifetimes. But if you count those atoms, the most abundant atom in the universe is hydrogen. Right? One proton, one electron. I'm using terms we haven't defined yet. We will define them. The next most abundant is helium. So, and where are those located? Those two elements. Predominantly in stars. You find some in gas clouds, but most of them are in stars. And then the other 0.1%, less than 0.1% are the other elements. So atom by atom count, not mass, but atom by atom, 91% hydrogen, 9% helium. If we look at atom percent in the Earth's crust, we get a different story. Right? Earth is a rocky planet. By the way, what does planet mean? Anybody know? It's from the Latin planeta, which means wanderer. What the observers, the ancient observers, found that some of those stars up there were moving relative to their neighbors, and they called them planeta. Most of them turned out to be what we call planets now, like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto got kicked out. It's now a dwarf planet. But if we come back to Earth, in the Earth's crust, most on the atom percent, most of the elements in the Earth's crust are oxygen. That's because most of the metals form oxides. Silicon, which is dominant, right? It's 20% silicon in the crust, and oxygen, right? If you want some silicon dioxide, you know where to go, right? Go to the beach, right? Wiggle your toes in the sand. That's silicon dioxide. And then there's aluminum, is a substantial percentage of the Earth's crust. So most of the soils that we encounter in the upper layer where we grow our crops are what we call aluminosilicates. That's the matrix. And then other nutrients are mixed in with those. We have hydrogen at almost 3%. Now, when we're talking about the Earth's crust, I think they're including water also. So that would make hydrogen a significant component. Even if we discount the oceans, there's a lot of water in the interstices between the soil and rock particles. I used to live next door to a mining engineer. He was retired, and he would tell me stories. He says, you know, we don't need to impound water on the surface. He says, you just sink a well anywhere in southern West Virginia, and you'll hit a flooded mine, an abandoned mine, and you get all the fresh water you want. Now, there might be some dissolved, undesirable stuff like sulfur, depending on where you're located. But he said, we could export it. There's so much water down there. Anyway, there are other elements. Calcium, magnesium, iron, sodium are major components, and then all the others. So the major, in the Earth's crust, oxygen is it. And then silicon are the two major ones, and that's 80% of the elements on the atom percent in the Earth's crust. All right. So we talk about chemical symbols. All right. When you start memorizing those, you're going to notice that their chemical symbols have either one letter or two letters. If they have one letter, like hydrogen, it's always capitalized. Right? If they have two letters, the first letter is capitalized and the second letter is small. So this is hydrogen, that's helium. If you are the type of person that likes to block print everything, right? And you write this like that, that's nothing. There is no element in there with that symbol. What I'm saying is, that's right, and this is wrong. The other thing you'll notice is that some of the elements, the symbols bear a resemblance to the English word. So hydrogen is H, that makes sense, capital H. Barium is Ba, that makes sense. Cobalt, Co. But lead, where does Pb come from? It comes from the Latin. Lead in Latin is plumbum. There's your Pb. And by the way, plumbum in Latin means heavy. So it's appropriate. Silver, Ag, that doesn't come from silver. Ag is argentum, which is Latin for silver, Ag. Many of the symbols are derived from the Latin. You just have to learn what they are. Potassium is K for calcium. Okay? There are several like that. Iron is Fe, Latin for ferrum. Let's see. Copper is cuprum. So if you say copper should be Co, no, that one's already taken by cobalt. So we say cuprum for copper, Cu. All right. So how about the size of an atom? Atoms are very, very small. So our example here, say in 1 inch distance, if you line the atoms up, you could put, give or take, depending on which atom you use, 254 million atoms in an inch, a straight line. So they're very, very small. And the atom is the smallest unit of element that retains the properties of the element. Right? So we've identified what the element is. Now, if we have it and have it and have it and have it, keep subdividing, we get down to 2, break them apart, you got 1 atom of that element. Molecules are combinations of atoms, compounds. Well, they don't have to be compounds. They're combinations of 2 or more atoms that behave as a single unit. So you could have a molecule of nitrogen, which is not a compound, but it is a molecule because the nitrogen molecules behave independently. Or you could have a molecule of water, which is a compound. And these water molecules behave independently. Now, if we have 2 atoms, this is diatomic. It doesn't matter what the atoms are. If there are 2 of them, it's diatomic. If there are 3 of them, 2 hydrogens and 1 oxygen, it's triatomic. And I guess if there are 4, it's quadratomic, but usually if you get to 4 or above, we just say polyatomic. Okay? Now, not to be confused with the number of atoms is the molecule is composed of 1 type of element. If it's 1 type of element, it's homoatomic. It's the same atom. So this one is homoatomic. Right? Our other example is phosphorus or sulfur. Those are all homoatomic molecules because there's 1 type of element only. Obviously, heteroatomic would have more than 1. This would be heteroatomic. It's triatomic, but it's heteroatomic because there are 2 or more different elements in the composition. Okay, we're using generalizations there. A could be anything, B could be anything. So the first one is heteroatomic and diatomic. And then B is triatomic and heteroatomic. All of these are heteroatomic. Okay. Classify. What is that? Xenon. It's a noble gas. Okay. Noble gases generally don't react, but they can be forced to react. And this one was forced to react with fluorine. So Is it diatomic or triatomic or what? Well, it has 5 atoms. It's pentatomic. Is that animated? Yeah, pentatomic. Is it homoatomic or heteroatomic? 2 different elements? It's heteroatomic. Is an element or a compound? Obviously, it's a compound. All right. In the interest of time, I'm going to skip these. All right. Chemical formulas. Well, that's a chemical formula. Um, let's see. Well, I don't have a, get my hard copy here. I don't want to steal my own thunder. All right. It may come later, but I'm going to give it to you now because it is the stream of consciousness. When we write the element symbol, and I'm just going to use an X because there are no elements up there with just X. This is a substitute for anything. There are 4 positions around that element symbol that are reserved for information. This position up here is reserved for charge. Right? So if that element is charged, it's an ion. If it's neutral, it's just the element. And you can either leave, you don't have to put a plus or a minus there, just leave it empty and it's neutral. Down here is the number of atoms. We've already used that in various compounds and elements. Like N2 is 2 nitrogen atoms. H2O is 2 hydrogens and 1 oxygen. We don't write 1, right? If you got the symbol, you got to have at least 1. So we just don't write 1. Over here, on the other hand, this is designated by Z is the atomic number, which is the number of protons. We're going to get this again, I think. Probably maybe chapter 3. Yeah, we'll get it in chapter 3. So you'll see this again. And this position is reserved for mass number. And the mass number is equal to the number of protons plus the number of neutrons. Yeah, we're going to get this in chapter 3, but I thought I'd put that in here because we need to know that subscript over here means the number of atoms. Okay. Let's see. So our example there, water we've used before, Ca3PO4 taken twice, is a more complicated formula, just as an example. And I think we're gonna get that more of that in chapter 3. So I'm going to leave a more complete description of calcium phosphate till later. But it just shows that you use subscripts to show how much of something. Oh, okay. So how many atoms of each element are present? In the first one, you have 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms in that formula. Okay. In the second one, iron 3 carbonate, you have 2 iron atoms, right? Let's see. Did I animate this one? I did. We have 2 iron atoms, but we've got a parentheses around the carbonate, CO3, and the 3 outside the parentheses propagates through the whole polyatomic ion. So we have 3 carbon atoms and 9 oxygen atoms. See how that works? Okay. All right. Oh, I think we're finishing up with chapter 1. Let's see. Let me check my time. All right, we're coming up on the end of the lecture period. So I'm gonna have to use up some of our lab period to do I'm gonna have to skip these concept questions. I'll just leave them up there long enough to get recorded.